Good morning. I'm Manoj Srivastava, Assistant Professor in Department of Computer Science and Engineering at the college, Akgec Engineering College. My today's topic is on graph data structure. In this particular topic, we will be discussing about the Dicastra's algorithm. And the course outline, as per the course outline, we have to study the graphs. The textbook that has been followed here, outlined here, as by Kamte, Introduction to Data Structure in C, Data Structure and Algorithm by Allman, Hofcraft and Allman, Data Structure using C++ by Tenenbaum, and Algorithm in C++ using Sedgwick. This course is designed especially for all those students who is studying the course that is data structure in their respective sections or respective branches or respective courses, that is BTech, MTech, BCA, MCA and all, and even BSc computer science they are doing there, they can go for this. In this Dicastra's algorithm, the main target is about where we have to implement is, and for what it is to be implemented and why it is implemented is based on, as the topic has been shown here, that is single source shortest path problem. This is the problem that has been discussed here, and based on this problem, what Dicastra has suggested about this algorithm and how this algorithm will help to overcome this shortest path problem without any problem, that has been discussed here. In case of single source shortest problem, the problem of finding shortest path from the source vertex V to all other vertex in the graph is to be find out here. As the graph, sample graph has been shown here, that this is a graph 6, 4, 5, there are different nodes. We can assume any of the node as a source node, because here prior to defining this source node, if we don't know about the source node, this algorithm cannot be applied here, though we can apply on any of the graph, but as the name suggests that it is a single source shortest path problem, so we have to decide the source node first, and that will be the starting point for the algorithm. Now, what exactly the algorithm says here is, in Dicastra's algorithm, Dicastra's algorithm is, as I earlier said, that it is for shortest path problem solution in a graph theory. It is a solution for shortest path, single source. Why it is single source? Because there are number of nodes, as we can see here in this graph, there are different number of nodes. Anybody can consider any of the node as a source. There are 6 nodes. Any node can be considered here as a source node. But in this Dicastra's algorithm, it has been suggested here to decide the source first, from where you have to start, and then you have to traverse to the rest of the nodes, so that we can decide the shortest path, single source shortest path from the given node or from the source that has been decided here. That is what has been explained here in this Dicastra's algorithm. And how it works, what will be the input for this Dicastra's algorithm, and what output we will getting here in this Dicastra's algorithm. So Dicastra's algorithm works for both directed and undirected graph. That means what? Directed graph means that is based on direction. An undirected graph is where no direction has been suggested or implemented. As we can see in the previous graph, this graph is undirected graph. There is no direction or specific direction has been marked here to suggest that this is a directional graph. If we simply put arrow in a particular direction, this graph will be converted to a directed graph. But when we consider a directed graph, a problem arises here. We have to also consider that there should be no any cycle in that graph possibly. If cycle is there, it will create some problem. Maybe the distance can be covered in a negative direction, or it can be have a negative weight comparatively to the specific position. But here we are not considering this. We are as it has been said here in this algorithm, suggested algorithm, they works on both directed and undirected graph. However, all the edge must have non-negative weights. This is also one of the specific condition here. Non-negative weight means only that, as we can see in the graph, as a note suggests here, that different weights have been assigned to the different node. It can be distance, or as per the circumstances, we can assign this node the value, whatever value we assign here, that is treated as a weight here. If we are considering a distance, it will be a specific distance unit. If we are considering in a some specific problem where distance is not required, but in a particular simply a circuit has to be followed. For example, if you are taking example as a in a home, if you are trying to what we can say here is electrifying our home in our circuit diagram. We are trying to make a circuit diagram. Based on that, we are trying to connect all the appliances in a particular home with an electric wire. In that case, also a distance comes here, but though it is a very small distance, so we do not consider the distance, but we simply track the path that can be shortest based on the distance. Similarly, some of the networking based problem can be there where no distance is required, but some other case, even in case of marketing, where marketing people used to sell and supply and sell it, in that case also some cases can be arises where distance cannot be the specific term that can be utilized here for finding out the single source shortest path problem. But though it represents here path, we will take an example with a distance only. Now, what will be the input in this particular? We need a graph, that is weighted graph, and in this graph, we as per the notation, it has been used here is G treated as a graph. This G is considered as a graph. This E is the edge and V is the vertex in that graph. Edge is the connecting point between two nodes, and V is the source vertex, we can say here, from where the vertex, from where the de Castro algorithm will follow to find out, such that edge weights are none, and also this condition that non-negative edge should be, the edge weight should be non-negative. You have to consider here as an input, and what output we will getting here from is the shortest path or shortest distance can be calculated by using de Castro algorithm. Now, what approach we are going to follow here is the algorithm computes for each vertex u the distance to u from the start vertex. I earlier said that the source should be known prior to finding prior to applying the de Castro algorithm. And from where the source is, we will consider the initial point or starting point, and from there we will try to move or proceed to the further nodes to find out the shortest distance as per the given graph. The algorithm keeps track of set of vertices for which the distance has been computed, and every vertex has a label associated with it, that is d, or it can be said as a distance will be the label. That means whatever, for example, if we consider the graph here, this is a graph example initializer graph. This A has been considered as a source and its distance has been specified here as a 0. That means this is the starting point. Whenever we will start with a graph, we have to represent this source with an arrow, that this is the source point. And we assume here or pre-assumption can be made here that whenever next node to be followed from this source node or to be reached to the next node, we initially consider that rest of the node will be very far, or it is at a very high distance from the source node. This is what we have to identify here, because we don't know what particular edge have low weight or which particular edge will help you to find the shortest distance. That's why we consider all the node at the infinitive distance, and after that we will apply the algorithm to find it out which is the shortest path in this algorithm. And this how it will be done here, we will come to know here. And that is what has been explained here. When vertex u is added to the cloud, that is into the graph, or while finding the path of the distance, means in a graph distance, while finding the distance of the graph, we consider this one. Means each node, the node which is present at the infinite position, and based on their level, based on their weight, whatever will be the shortest path, that will be updated to that node. Now we will see the pseudocode. As based on the pseudocode, what initially done here is, prior to doing this pseudocode, we will come to directly to the example, and then we will revert back to this algorithm, which will help us to identify the algorithm, each line, and justify with the example that how this algorithms or pseudocode line works here. Now we can see here in this graph, initially this graph has been initialized here with a particular distance, which is a source distance with a 0, and rest of the node with the infinite value. This and the edge weight has been given here. And one more thing is that this graph is directed graph. We can see here, this is a directed graph. From A to D, arrow has been followed here. From B to D, arrow has been followed. Means this arrow represents that this is a directed graph, and weight has been given. Weight, actually it is a distance from the particular node to the next node. How it has been identified that which will be the shortest path? Initially we have to mark it 0, the source node, and rest of the node to be infinite position. Now we will see from the source node what are the edges that is being connected to the different node in a particular direction. If it is if the edge is connected in opposite direction and reverse direction, means incoming arrow is there, that means that will be not considered as a path for the node, only outgoing, because source, from this source we have to start and move to the other node. That's why outgoing edges to be considered here. Outgoing directed edges to be considered here. Only two edges are there, that is from A to B and A to D, and the weight has been given here, 2 and 1. This weight will be after movement, that means after from source node to next node, whenever we will move, we will relax this node with a distance that has been marked on the edge. That means what minimum distance has been traveled from A to B is, that will be marked here. Similarly from A to D, that will be marked here. And this is how it will be done for the rest of the nodes. If there is no path, that node will be remain intact at the infinite location, because we do not have discovered that node, and we do not have any path which will be updating the weight or updating the distance from the source node. That's why that list will be left here. Now again, after reaching to the different nodes, we will follow from there as per the algorithm, and we will try, based on the shortest distance that has been traveled, we will try to move to the next node from the last node that has been reached with a minimum value. So in this case, we can see here D is the minimum value with a 1 distance, and from here we will try to find out the rest of the node that has been connected here. So in this case, we can see here that from D, position D, the rest of the node that can be traversed is C, E, F and G. B cannot be traversed because it is on direction of the arrow is in opposite, that is incoming direction. And one more thing will be happen here. If this would be the path, then it will form a cycle, which will create a problem, and which is one of the conditions that is to be not followed here. Now, starting from the D, when we will move to the C, the edge value or weight of the edge is 2, that is distance is 2. Now, whenever we will relax this C node, we will simply add the weight of the D node that has been relaxed earlier from the source node, and now when relaxing this C node, we will add this 2 with the 1, which will give you the 3. Similarly, we will do for all other nodes, and we will relax the rest of the nodes from the D position. That is what has been done here. That is from distance, the distance of C from the source node A, D and C is 3. We can simply identify it by the diagram also. Similarly, rest of the diagram also shows the same thing, and means all the node has been relaxed here. Now again, what happens here is, in this example, this is the actual path or actual root node as per the algorithm, the Castro algorithm, with the shortest distance. Now we have to find it out simply by visiting all the nodes and identify which is the shortest from this source node. So now whenever we try to find it out or try to verify that this is correct or not, we can easily verify simply by following the algorithm. Now in the next case, this is the example. Earlier it was the F position was 9, but if we try to traverse with some other path, we can see here, in case when the source D was source and the path traverse was 9, 8 plus 1 8 gave 9. But if we try to follow this path, that is A, D, C and F, this will give you the smallest path. So we have to optimize this graph till we get the shortest path from the source node. This is what algorithm repeatedly will do in their algorithm and will be followed. That is what to be done here in this algorithm. From here we can see that the distance of F is 8 now. That has been, if the earlier distance is high, that will be relaxed with the lowest distance and the lowest route path which has been followed here. Similarly, we can see if this path will be followed from some other location, it will give even less. For example, A, D, G and F. If this path will be followed, it will give even more optimized solution as per prior to the previous answers, that is 8 and 9. So this has been relaxed to 6. The distance has been relaxed because this path has been followed here, starting from the A, D, G and F. So, by following this route, we can see that F has been optimized, or it has been reduced, or it has been relaxed to more shortest distance. And this is how the shortest distance. And now we can check the rest of the nodes, that if any path with a less relaxed path is there, or a less relaxed node is there, then we can do till all the node is been relaxed to the minimum or shortest distance, and that will be the final solution for the. Now we will go to the algorithm here, and we can see here that what was happened here. In this algorithm, we can see here that the Castro says that we have to consider two nodes. V1 V2 will be the input, that is starting source node, and one will be the next, that will be this node. For initially, what we have to do here is, for each vertex, we will assign from initially whatever the vertex that has been initialized as a source node, that will be initialized with a 0, and its distance will be 0, and rest of the vertex rest of the nodes have the infinite distance. That has been done here in this code. By using for loop, we can initially the distance of source node as 0, and rest of the nodes, that is v node, or previous is equal to none, or if there is none, then we can say none, otherwise it will be infinity, and list all the vertices that has been taken in the graph. Now next step is what we have to find it out, what is the shortest path from the source node. For that we have to move from source node to the next node, that is while list is not empty, that has been created with all the nodes, that list is being said here. Means as per the graph, maybe 100 nodes may be there, or more than that will be there, even less nodes will be there. But as per this example what we have seen just now, there were 6 nodes. That 6 node, that is we can mark it here as a ABCD, or any number can be assumed here. Then based on that, this list consists of 6 node, and in this 6 node we will remove one node at a time and try to find it out what is the distance from the source node. Mark V as a known. For each unknown neighbor n of V, distance you have to take. This is the relaxing distance of the nearest or neighbor node from the source node. Means what you have to do here is you have to consider the distance of the node plus edge weight. What was the edge was having weight. Means earlier if we take the example here, if you see the example here, what is happening here means when you are moving from A to D, if you are considering the D from the list, that is next node is D, then from A to D the level consists of weight 1, and initially A has 0 weight. So whenever we will move to the next node D, we will add this weight of the previous node and weight of the edge. This will give you 1, and this D will be updated with the 1. That is what has been explained in the algorithm. That is distance plus edge of the vertex, or edge of the edge weights. If distance is smaller, then now we have to check with the condition. If distance is smaller, then n's distance, n distance is equal to distance, and n previous distance is equal to v. Now this code specifies what, based on the condition we have to check it. What we have to check it here, that which next node has the smallest, as we did in this example, that in very beginning it gave 9 as a, when it relaxed the f node from source node A, D and F, it gave 9 as the weight. But after again trying some other path, that is this path A, D, C and F, we got this relaxed to 8. Again similarly we tried with another path, that is A, D, G and F. This F node was relaxed with a weight 6. So this is what will be done in this algorithm using the Castro algorithm. It will be relaxed to the node will be relaxed to the minimum weight and with a minimum path distance. This is what this algorithm explains here. Now we will consider another example. Another example here, we are using a graph and we are trying to solve this problem with the help of matrix method. Same procedure will be applied here. We have to take the source node and rest of the node will be treated as at the infinite location, and the list that has been marked here in the algorithm, the Castro algorithm, will be initially will be there in the list. Since A is the source node, we take the position or distance of the A as a 0 and rest will be treated as a infinite. Now starting from the A node, we will try to move to the node in this directed graph, which is the nearest neighbor that has been connected with the source node. So there are 2 nodes A and C, and these 2 will be updated with by adding this 2 weight, 0 and edge, that is weight of the A previous node and weight of the edge that has been connected with the next node. and this will be updated with the value 10 plus 0, that is 10. So this is what we will see here, and in this adjacency matrix it will be updated, that is from A to B. A to B the distance is 10. Similarly from A to C it is 3. As we can see here, 3 is the weight of this edge and 0 is the weight of the source node. When we apply the algorithm, we will see that the weight will be updated with the 3, and rest because there is no direct path to the D and E, it will remain as it is intact, that is infinite distance, present as an infinite distance. Similarly, again we will consider here in this second row which one is the shortest distance or lowest value, that will be considered as the next node from where we have to move to further to the next neighbor node to find it out the shortest distance from the last node that has been traversed here. The node with a minimum value will be considered here. We will not consider this 10B node. We will consider C node because C is having the weight less weight, that is 3, and this will be included in the path here. So we can see here A was the source node. After that it was traversed to the C because C was the shortest path in this case. Now from the shortest path C, if you will try to find it out, this 3 plus 4, this 10 is updated to 3 plus, because edge C to B, edge having weight 4 and the source node C having weight as a 3. So this will be updated to 7 by simplifying it. And similarly we can see here C to E, this will be updated to 5, and because C and D is also having some path, this will be also updated to 8 plus 3, that is 3, 11. So this is how all the node will be get updated. But next comes what? We have to check it that which node, from which particular, from which previous node, the next node having the shortest distance, that is to be identified here. Now after identifying that this B, D and E, we saw here that this has been updated with the 7, 11 and 5, and out of these 3 nodes, which one is the node having shortest distance, we can consider that node and we will add into this that is shortest distance source node, and this E will be added here. Now from the E we will try to find out which will be the next shortest which node having the position at the shortest distance. So from here we can identify that 7, that is B, 3 plus 4, 7. From C it has been, and from E, as C was this, it will remain intact, and this 5, this infinite, that is earlier it was 5, that this has been updated to E. And in case of next, here we have considered E, and from E location if we try to check it out that which node is at the shortest distance, this will be calculated from 5, and if we consider this B node, what is happening here is out of this 7 and 11, because 5 has been already done here, 5 and 7, 11 and 5 was the shortest distance that has been traversed. After that nothing can be updated to the next node, because if we check from the this E position, 5 plus 9 it will come to 14, and since it is already at the shortest distance, so it will not be updated. This will not be updated to 14. This will be increase the distance of the path. That's why it will not be updated. This will remain intact in this graph. So after relaxing this one, we will try to find out which one is the node that is having minimum value, next minimum value. So from here we can identify that 7 is the next minimum value. So in next step in this matrix method, B will be considered as a node here, next node, from where you have to identify what will be the shortest distance for the remaining of the node. So from here we can identify from B that when we will consider this S to D, by adding this, we will update to 9. Earlier it was 11, 8 plus 3, it was 11 from C to D. Earlier it was 11. Now from B to D, it has been updated to 9. This comes the shortest path for this particular graph, and how to identify that from the source, what are the nodes at the shortest distance. It is very simple that we have to either you follow the ascending order list in the matrix, that is starting from the 0, that is source node A. Next node will be the C node, that is having the distance of 3. From here it is next node is 5, which is having shortest distance, that is E, and from similarly after that 7 and 9. From this is how the path will be completed in this graph, and just by using matrix method we can identify, or we can apply the Dijkstra algorithm to find out the shortest distance, single source shortest distance. Earlier we done by manually simplifying the graph. Here as simplifying the graph with the help of matrix. So both the approach can be applied to solve the shortest distance path problem by using Dijkstra algorithm. And as per the pseudo code here, this is the main code which is being used in the algorithm to relax the node. And how this node can be relaxed here is, for each vertex belonging to adjacent U, what you have to do here is we have to change the distance. We have to verify the distance, that this distance is greater than distance of previous node plus weight of the connecting node. If it is greater, then the D will be dV, that is the next node, will be updated with the whatever sum of the value. If this one is greater, means the next node, upcoming node, having higher distance, and when we are trying to find it by the some other path, if it is its previous node and its weight is having less value or less shortest distance, that distance will be updated in this case. That is what is called relaxing. This is what the relaxing is done in the Dijkstra algorithm. This is the relaxing criteria, is the important criteria that has to be followed here. And this is how topic completes. Complexity will be, because we are using vertex and edges, so total time complexity will be V. So as number of vertex is V and we have to traverse to each vertex, so complexity will be vertex is square, that is higher value we can consider here. And time complexity in priority, if you are considering a priority queue, E of edge E of log V will be the time complexity. Thank you. Thank you so much for the topic.